Okay, so this is a diagram of the launcher that I just showed you set up in the classroom, and we're going to talk about how we can predict where that ball's going to land. But before we get to that point, let's talk about this conceptually a little bit. Let's talk about the motion of this perfectly horizontal launch, which we sometimes call a bomber problem. So, if we look at the old motion map that we drew for an object that was launched from the ground, traveled to its apex, and came all the way back down to the ground, what we notice is the second half of this launch looks exactly like the bomber problem. And that's an important conceptual thing to understand. So in other words, if I go and I erase the first half of this launch, we realize that this is the exact same motion as that. And so that's one of the keys to really grasping and understanding the bomber problem, is that it's really just the second half of a full arc going from ground to ground and going up to the apex in the middle. If we think about the velocity vector at the start of the launch, we see that it's just like the apex here, where all the velocity is in the x direction, none of it's in the y direction. And at the end, we now see that that x velocity has remained constant because we've got constant velocity in the x direction, but the y component of velocity is increased because gravity has accelerated it in the downwards direction. All right, so let's think about this now from a problem-solving perspective. We thought about it from the conceptual perspective. Now let's approach it from a problem-solving perspective. There's really 4 steps to solving a problem like this, a kinematics problem. And the first step is drawing a diagram and labeling values. So there's our diagram, and now let's start labeling some values. First of all, as I mentioned in the video, the launcher fires at a velocity of 4.8 meters per second. I also mentioned that I measured the height of it to be 1.18 meters above the ground. And then finally, our goal is to try and calculate what the range of this is. And range is a special way of saying the distance traveled in the x direction. So that's our diagram. The next thing we need to do in our values, but we also need to set 0, 0. Now, I recommend that you set your origin 0, 0 right down here. And the reason I recommend that is because by putting your origin 0, 0 down there, everything is positive. All these y values are positive, and all these x values are positive. So all the direction that the ball is going to travel is in the positive direction. Now you could certainly put your origin 0, 0 anywhere you want, like right up here or right here. But at those locations, you're going to have some negative values, right? You'd have some negative x values here, and you'd have some negative y values there. So you can put it anywhere you want, but if you put it on the ground, then you're always going to get positive values, which is a little easier to deal with. The second step in solving a problem is to identify the initial and final moments in time. For this problem, since we're starting up top, that's our initial moment, and our final moment is just before it hits the ground. I strongly recommend that you draw the velocity vectors at the initial and final moments. I've already drawn it at the initial moment because we know it's the top of the apex of the full path, and at the end, the velocity vectors would look like that, where the x component of velocity remained constant, but we grew a y component of velocity because gravity sped it up as it fell towards the ground. All right. The next step is to list our variables. We know that we list our variables like this, and this represents the constant velocity model in the x direction and the accelerated model in the y direction. We know that the initial x position right here is at 0 in the x direction because it's not to the right or the left of the origin. We know that we're looking for the final x position because that's the end of the range. We know that the velocity, the constant velocity it's going to travel in the x direction is 4.8 meters per second because that's what it's launched at, and it's launched entirely in the x direction, pointing entirely horizontal. and we know that it's not accelerating in the x direction. We know that it starts at a height of 1.18 meters, so its initial position in the y direction is 1.18, and it's going to land on the height of the floor, so it's going to land at a height of 0. So the final position in the y direction is 0. And we know gravity is accelerating at negative 9.8 meters per second each second. Now, there's one more value we know, and it's the initial velocity in the y direction. And the initial velocity in the y direction is 0 meters per second. And that is a unique thing to any bomber problem. And the reason it's unique to a bomber problem is because the velocity initially starts entirely pointing horizontal, entirely in the x direction. None of it's in the y. If this were tilted up a little, then you'd have some in the x and some in the y. But because it's perfectly horizontal, for a bomber problem, all the velocity is in the x and none of it's in the y. All right, the next step is to solve. So let's solve for our unknowns. If we know that our y direction, we've got the acceleration math models. So here they are. We've got our 3 mathematical models for accelerated motion. And if we go through them one by one, we can think about which values, what unknowns we have and what knowns we have. So we can see that we've got all these in this equation. We've got all knowns except for time. Time is unknown. If we look at the next equation, we discover that we've got 2 unknowns. So that's not going to be a good one to work with because we've got 2 unknowns. And then our third equation, we've got 1 unknown again. So we could use that one. In fact, I'm going to have us start with that first equation. So let's go ahead and solve for the final velocity in the y direction. When I solve one of these problems, the first thing I do is I cross out anything that's 0. Then I go ahead and I plug in my numbers, and then I go ahead and solve. Now the trick to this is that we're taking a square root as our last step, which means our final answer is either positive or negative 4.8 meters per second. Because this final velocity in the y direction is pointing down, we know that it's not positive 4.8, but rather negative 4.8 meters per second. And so there we have it. That's our final velocity in the y direction. Now let's try and solve this equation over here. First we cross out zeros, then we plug in our numbers, and then we solve for our unknown. Once again, we see that we're square rooting is our last step, which means that the final answer could be positive or negative, but time, of course, moves in the positive direction, so time is positive 0.49 seconds. All right, let's go ahead and write those down here where we're maintaining our equations. And now let's look at the x direction. In the x direction, we know that we've got our constant average velocity model. So that equation looks like this. Average velocity is constant velocity, which is change in position over change in time. Well, let's see. Well, the only unknown, we've got our constant velocity, and we know our time, so our only unknown is the change in position. Plug in our values, solve for our range, and there we have it. We've now predicted that the ball is going to land 2.35 meters away from where it started in the x direction. All right, I hope this was useful and it made sense, and let's go test it out.